So I introduced you to an example of the inverse Laplace transform, but I thought you guys are just going to think I'm making it up. Obviously I'm not though, because this is obviously a real mathematical discipline. But I wanted to introduce you to the main inverse Laplace transforms that you should be able to recognize, and the main ones that you'll come across when solving inverse Laplace transforms. Well, at least basic ones. I'm not going to go over convolution theorem, which is just another branch of the inverse Laplace transform. It's like a little, it's pretty cool to be honest with you, but I don't think I'm going to go over that. I don't actually know it at the moment. I'd have to learn it. Doesn't take long though, let's be honest. I'm a genius. No, I'm kidding. So, I know these are going to look foreign as hell to you, but when I start solving inverse Laplace transforms that have these kinds of forms, you'll see exactly what they are and how to sort of get them into this form. So, the long story short, I'm going to explain that an inverse Laplace transform, all it is you algebraically manipulating it into one of these forms. So then you can automatically determine the answer. So basically the idea is if you take the inverse Laplace of this, you get this. If you take the Laplace of this, you get this. That's how it works. So this is one inverse Laplace transform, and then if you take the inverse Laplace transform of this one, so let's just say this is s squared. You can rewrite that as s to the 1 plus 1, which means that's 1 factorial. And then that means your answer is going to be t to the n. Well, your answer your n value is 1, so it's t. So if you had 1 over s squared, your value is t. If you had 1 over s cubed, it's t squared, and so on and so forth. And if you didn't have a 2 up here or whatever, so let's just say I had s cubed, so that's like s to the 2 plus 1, right? And if I didn't have the value of n, what I would do is that I have to multiply this 2 factorial, because I know that's what n is, because s to the 2 plus 1 is s cubed, and I'd have to multiply this whole inverse Laplace transform by 1 over 2 factorial, and then I'd have 2 factorial, and then my answer would be t squared. So, but my answer would actually be t squared multiplied by 1 over 2 factorial. So that's how you do it. And this is another inverse Laplace transform. So I have some constant a over s squared plus a squared. So that's sine of at, and I'm going to show you how to manipulate that as well. You have the inverse Laplace transform of s over s squared plus a squared. That's the cos version. So that's the difference between cos and sine. If you got a constant on top, it's sine. You have an s on top, it's cos. That's the general idea. And this was in my first example. The inverse Laplace transform 1 over s minus a is e to the at. That's pretty much the easiest one on the planet. Sorry, my light just decided to fall down. So here we go, an inverse Laplace transform of b over s minus a squared plus b squared. That's e to the at sine of bt. As you can see, you see how I have a constant b in the numerator? That's where that's coming. That's obviously the sine part, because you remember up here, if you have a constant up top, that's the sine part. So you can see where it's coming from. And s minus a, well, that looks familiar. Oh wait, that's coming from this inverse Laplace transform, so that's e to the at. So that's how, so you can see sort of where these Laplace transforms are coming from. So you sort of can, like, you know, use your matching memory and realize what's really going on. So, and the same thing with the inverse Laplace transform of the cos, except the only difference with cos is you have to subtract a, so you have to make it the exact same as this for it to be valid. And then it'll be e to the at cos bt. And the last inverse Laplace transform is very similar to the first one I showed you, n factorial over s minus a to the n plus 1. So that you know that this is t to the n e to the at. So you can see exactly, like, it's not hard to recognize that these are all interrelated with each other. But anyway, these are my top recommended. So the reason why I make this video is not only to introduce you to the table of inverse Laplace transforms, but also to make you recognize that if you're in the middle of an exam, like I will be in a month and a half, I don't want to be having to look at the table to find out what the inverse Laplace transform is and like what it relates to. Like if I've got an inverse Laplace transform 1 over s minus a of that form, I better not be looking at a table to find out that it's e to the at. 1, because it's a waste of time, and 2, it shows that you don't actually really get it. At least that's what I think. So I believe that you should memorize at least 80% of these. I know that's just a number I pulled out of, like, you know, the rear end, but if you could memorize all of these and actually understand what you're doing, which means you've probably done a lot of inverse Laplace transform examples, then that's fantastic. But if you can memorize at least most of these and forget maybe 1 or 2, then you're on the right track. I always forget this one, and I usually forget this one, but I memorize everything else. So that's how I am at the moment. But yeah, so I don't recommend, like, the table is definitely useful if you're stuck, but you shouldn't rely on the table to know what the inverse Laplace transform forms are. You should be able to recognize them straight away and manipulate them into the form you want to. And that's all I've got to say. The next videos obviously will be examples. This is just a video to introduce you to the table and show you that my inverse Laplace transforms are literally just coming from this table that I've got right here with all of these formulas. That's where my answer is coming from. Anyway, I'm beating the dead horse, aren't I? I'll see ya.